So this is our last example for today. It's also the last objective in Unit 2, so it kind of brings together a lot of the techniques. So this is an example that is going to call upon you to do just about everything that's important in Unit 2 is going to come up in this last example. So in this example, we need to solve this equation. We need to get the x by itself. And the equation has a polynomial on both sides. And on the left-hand side, that polynomial happens not to be simplified. It's x minus 3 quantity squared. So we need to figure out a strategy that can let us get this x by itself to solve this equation. So what's it going to look like? First of all, because this equation has both x squared and x terms in it, right? It's got that 2x squared over there. It's got a 10x in a separate term, so it's not like terms. That means that it's not going to be enough for us just to use the reverse order of operations to make this happen. We're going to need something more. And this something more is what I call the quadratic strategy. This is a strategy that's going to work for solving any quadratic equation whatsoever. We're just going to need to keep our options open on how to do it. And the first step, and this is the one that everyone forgets, the first step is to collect all of the terms in this equation onto one side of the equation so that the other side has nothing. So the other side is 0. If we don't do that, then chances are everything that we do afterwards is going to be fishy because all of the quadratic solution methods that we know in this course to solve a quadratic equation, except for the simplest, which is the square root method, which is almost never usable unless you do something really fancy. All of the methods that we care about are going to require us to have that 0. So if we don't do this first step, everything else we do afterwards is going to be nonsensical. Once we have that 0 on one side, we'll have to simplify our quadratic. And when we simplify it, we're going to get it into what's called standard form, where it's a trinomial with 3 terms, one of which has a square in it, the second of which has a single power of x, and the last has just a constant. And the other side of the equation is going to be that 0. Again, important. Cannot be overstressed how important that is. Once that's done, now we can take a short detour, and I like to do this whenever I'm working with a quadratic equation. We're going to compute what's called the discriminant of the quadratic. The discriminant is an expression which just takes the coefficients, the a's, b's, and c's from the standard form, and smooshes them together in this fashion, b squared minus 4 times a times c. That quantity is going to tell us what strategy will work for us going forward. If that quantity is a perfect square, so if it comes out to a number like 100 or something like that, then that means we should try to factor because factoring over the whole numbers is going to work. If it's not a perfect square, for example, if it's something like 7, or if it's something which is negative, for example, then factoring is not going to do it for us, and we're going to have to use a second technique called the quadratic formula, which we're not going to dwell on right now. It's something for later on in the course. So this is kind of a way to tell us whether factoring can be expected to work for this problem, or whether factoring is just not going to be feasible. Whichever of those methods that we choose, especially if it's factoring is going to let us split apart our equation into 2 simpler equations, which we can then solve using the reverse order of operations. So this is what I like to call the quadratic strategy. First, ship all of the variable terms onto one side, all the terms, period, onto one side of the equation, which leaves the other side equal to 0. Then simplify. So you can identify what we call the standard form of the quadratic, ax squared plus bx plus c equals 0. You can pull out the coefficients a, b, and c. Then we'll take a quick detour to compute the discriminant, b squared minus 4ac, so that we can be sure if that discriminant is a perfect square, that means that we can get away with factoring this example. If it's not, then we're going to have to go for a different technique. If we're able to factor it, then we can split it apart and solve. So let's get started. First, we're going to collect all of our terms in this equation onto one side. And as always, the way to move terms from one side of an equation to another is by adding or subtracting. So I'm going to take all the terms on the right-hand side of this equation and subtract them so that the right-hand side becomes 0. When I do that, the left-hand side is going to be that same x minus 3 quantity squared, but then minus 2x squared plus 10x minus 4. Okay, great. So now we have that all-important 0 on the right-hand side of our quadratic equation. That is so incredibly important that if we didn't do this first, chances are we would do a bunch of nonsense next. Now let's simplify. Because we have a bunch of stuff going on that left-hand side of the equation, let's try and boil it all down into a quadratic in its standard form. Well, first we got to get rid of those parentheses around x minus 3 squared, avoiding the most common error, which is to try to distribute the power over subtraction, which again, never works. Rewrite it as a product, x minus 3 times x minus 3, which we can distribute, multiplication over addition, or FOIL if you like, to get x squared minus 3x plus 9. Combining those like terms in the middle makes it x squared minus 6x plus 9. So the expression that started in the parentheses, x minus 3 quantity squared, is really x squared minus 6x plus 9. Then we also have this minus 2x squared plus 10x minus 4 on the left. And the completion of our simplified left-hand side requires us to combine like terms. Well, where are my like terms? I've got a pair of terms that have x squared as the variable factor that I can combine. I have a pair of terms that have x as the variable factor that I can combine. And I have a pair of constant terms that I can combine. When I do that, I'll get x squared minus 2x squared, which is negative 1 as a coefficient, x squared. I'll have minus 6x plus 10x, which is going to give me plus 4x. And I'll have plus 9 minus 4, which will give me a plus 5. Right-hand side of my equation is still 0. And now I have my quadratic in its standard form, ax squared plus bx plus c equals 0. If a, the coefficient of my quadratic term, is negative 1, b, the coefficient of my single power of x, is 4, and c, my constant term, is 5. So now I know what a, b, and c are, and I have my quadratic in its standard form. One more thing that I usually like to do if I can get away with it, though, is to take the whole equation and divide it by that leading coefficient, divide it by the value of a. In this example, a is negative 1. It turns out to be really easy to divide something by negative 1. So I'm going to do that, and you'll see why that helps in just a moment. If I divide negative x squared by negative 1, I'll just get positive 1x squared. If I divide 4x by negative 1, I'll get negative 4x. And if I divide 5 by negative 1, I'll get negative 5. So now we're in a situation where we have a quadratic equation where the left-hand side is a quadratic whose leading coefficient is equal to 1. So a is equal to 1 now, which is really nice. B is negative 4. C is negative 5. So now let's pause and figure out whether we can expect factoring to be a valid way to approach this problem. We'll do that by computing the so-called discriminant. This is an optional step. If you can look at this and see right away that, oh, sure, I can factor it, then you don't have to do this part. But this is a useful step, especially for later on if we decide to use different techniques instead of factoring. So what is the discriminant? B squared minus 4ac. Well, what we're supposed to do here is square the coefficient that we got for b, multiply the coefficients for a and c by one another, and then multiply them by 4, and then subtract the results. Well, b was negative 4. A was 1, and C is negative 5. Being careful not to screw up the signs, negative 4 quantity squared is positive 16. And then I'll have minus 4 times negative 5. That's going to be minus negative 20. Minus negative 20 is the same as adding positive 20, and so I'm going to get 36 for the discriminant of this quadratic. What does that tell us? Well, it tells us two things. The first thing we notice about it is that it's positive. Because the discriminant is positive, that means that our equation is going to have two real number solutions. So we can expect that the answer to this problem is going to be two different values of x that are both real numbers. But the second thing we notice about it is it's a perfect square. 36 is 6 times 6. Right? And therefore, the solutions are going to be nice whole numbers, which means that we should be able to use factoring to get us home. So let's factor. How does x squared minus 4x minus 5 factor? Well, because that constant term is a negative, that means that we're going to multiply by opposite signs, x minus something times x plus something. After all, the only way to get a negative constant term is to multiply a negative constant by a positive constant. So we'll write x minus something and x plus something. Now, what do those somethings need to be? Well, they need to be factors of 5. Since 5 is a prime number, that turns out to be an easy question to answer. It's got to be a 5 and a 1. And how do we place the 5 and the 1? Which one goes where? Well, the fact that our middle term has a negative 4 as a coefficient, that sign goes with the bigger of the two factors that we're going to multiply by. So the negative is going to go with the 5, and so we need x minus 5 and x plus 1. Great. So we factored the quadratic on the left-hand side. The right-hand side is equal to 0. Now we come to the entire point of doing the factoring exercise in the first place. This now allows us to split this equation into two simpler equations to solve. We can split the first factor, x minus 5, to have its own equal 0. And we can split the second factor, x plus 1, to have its own equal 0. And we've traded one challenging equation for two very simple equations, each of which we can solve with one step in the reverse order of operations. Adding 5 to the first equation on both sides gives you x equals 5. Subtracting 1 from the second equation on both sides gives you x equals -1. And there is the solution to this quadratic equation. So there was a lot going on here, so make sure you don't miss the overall strategy. The first step in the overall strategy is any quadratic equation, you got to get everything to one side and a 0 on the other. If you don't do that, then what follows is likely to be nonsense. Once everything is on one side by subtracting, then simplify. Try and reduce your quadratic down to its standard form, ax squared plus bx plus c. Along the way of doing that, we had to take a power of a polynomial, x minus 3, the quantity squared. So we had to remember that we can't just distribute the exponent. We needed to rewrite it and FOIL it. Afterwards, we combined like terms, and we got minus x squared plus 4x plus 5 is equal to 0. When convenient, it's always a good idea to try to divide by the leading coefficient, which in this example was -1. If we do that, we then get what we call a monic polynomial, one which has a leading coefficient equal to 1, and polynomials with leading coefficients equal to 1 are always much easier to factor. And we know that factoring is going to work in this example if we compute the discriminant, because we discovered the discriminant was 36, which is a perfect square. Because the discriminant was a perfect square, we know we can factor. And when we go to do the factorization, we learn that x minus 5 times x plus 1 is a factorization of our quadratic, which when you set that expression equal to 0, we can split into two pieces. One piece that says x minus 5 is equal to 0, which gives us the solution x equals 5. And the other piece, x plus 1 equals 0, which gives us the solution x equals -1. This overall quadratic strategy is going to be something we come back to later on in the course when we want to approach quadratic equations that might not be able to be factored. So when we learn the quadratic formula, the first parts of this strategy are going to be the same. Collect all terms to one side and simplify to standard form. But then the second part is going to be different. If we discover the discriminant is not a positive perfect square, then we're going to have a different strategy for how to find its solutions. But in this example, we could have skipped that step and just said, oh, I can factor this, factored it, split it up, and solved it. But we can't do any of that stuff without that step number 1, which is move all your terms to one side of the equation, leaving a 0 on the other.